Hello and welcome to Unit 9. This is our next to last unit. So we're going to talk about a couple different things this unit, solutions and then acids and bases. So we're going to start today by focusing on solutions. So by definition, a solution is a homogeneous mixture of two or more substances. Now, we used this term a long time ago. And homo means same, so a homogeneous mixture is the same throughout. Every sample from that mixture is going to be exactly the same. And a solution has different properties than its individual components. So an example of a solution you can think of is salt water. So if you have salt all by itself, that's going to be different than water all by itself. But when you combine them together to make a solution, salt water, that also has different properties. So it's going to be different. But you're not going to be able to see individual pieces of salt. It's all dissolved throughout. And so it's homogeneous or a homogeneous mixture. We have two parts to a solution. The first part is the solute. The solute is whatever substance is actually being dissolved. So if we're still using our example of salt water, then salt is our solute because it is the thing being dissolved. It's in the smaller amount or the smaller part of the solution. And then the solvent is whatever substance is actually being dissolved in. It's doing the dissolving. It's in the greater part. So for salt water, water is our solvent. And I can tell you that water is the most common solvent. It is a very, very good solvent. Lots and lots of different things will dissolve in water. It's not the only solvent, but it's definitely the most common. And we've seen this before, actually. If you remember, we talked about aqueous. So when we have ionic compounds dissolved in water, we call them aqueous. That's what we were saying. It's a solution. It's something dissolved in water. All right. So that's probably the most common thing we think of when we think of solutions, is we think of a solid dissolving in a liquid. But that's not the only type of solution. Solutions can actually be between different or same states of matter. So solid in a liquid is like what we were saying, that's like salt water. We can actually dissolve some liquids in liquids. An example of that is isopropyl alcohol. So that's isopropyl alcohol dissolved in water. We can dissolve a gas in a liquid. That's like carbonated soda or any carbonated beverage. It's got lots and lots of CO2 dissolved in that liquid. We can actually dissolve solids in solids. Those are called alloys. An example of that is brass. That's a mixture of zinc and carbon all combined together. And we can actually have liquids in a gas. So water vapor in the air is an example of a solution with a liquid in a gas. So in order to form a solution, we got to break down two different attractions, and then we got to form a new attraction. So we have to break the solute interactions or attractions. So we got to put energy in to expand or break apart our solute. And remember, our solute is the thing being dissolved. We also have to put energy in to break the solvent-solvent interactions or attractions. Remember, the solvent is doing the dissolving. So again, if we're talking about salt water here, this would be sodium chloride. So we have to put energy in to separate out the individual sodiums and chlorines. And then our solvent would be water. So these would be representing water molecules. We got to separate those out so that they're spread apart. And then finally, we have to form a new attraction between the solutes and the solvents. So notice here, we now have the NaCl interspersed throughout the water. So when we form a solution, we got to break apart the solute, we got to break apart the solvent, and then put them together and form new attractions. Some terms we need to be aware of, and we've used these terms before when we were talking about double replacement reactions and precipitation. The word soluble just means that it will dissolve. So then insoluble means it will not dissolve. And thinking for a minute why something wouldn't dissolve, that's because it will take too much energy to break apart either the solute or the solvent, or there's no attraction between the solute and the solvent. So it just doesn't dissolve. So that's like our precipitates in our double replacement reaction. When we combined them and those two ions met each other and they were more attracted to each other than to the water, it formed a solid because it was insoluble. Our last term we need to know is solubility. So for any substance, it has a certain solubility. And what that means is the maximum amount that will dissolve in the given conditions. So that's going to change based on temperature, what the solvent is, what the solute is, or even will change with the pressure. So we have something called the solubility curve. And a solubility curve is a graph that tells us exactly how many grams of each of these different substances. So on this particular solubility curve, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 different substances listed. And if you notice, this axis is very specific. If you look at our y-axis here, the solubility is in grams of salt in 100 grams of water. So it tells us exactly how many grams of the salt or the ionic compound will dissolve in 100 grams of water at a given temperature. So for example, I've shown you here at 25 degrees, so this would be 25 degrees. If we go up to the potassium nitrate curve, we see right here that exactly or right around 37 grams of potassium carbonate will dissolve in 100 grams of water. So that's how we read these curves. So let's look at an example. How many grams of potassium chloride will dissolve in 100 grams of water at 30 degrees Celsius? So we have two things we need to look at. We need to go to 30 degrees Celsius, and then we know we're looking for potassium chloride. So I'm going to follow the 30 degrees Celsius line until I get to potassium chloride. And then I follow that over. This says 100 grams of water. That's what my axis says. So this is going to be 35 grams of potassium chloride. That's going to dissolve in 100 grams of water. Now, this next one says how many grams of potassium nitrate will dissolve in 300 grams of water at 10 degrees Celsius. So this time we're going to look at 10 degrees Celsius. We're going to look at the potassium nitrate curve. And when we follow that 10 degrees Celsius line to the potassium nitrate curve, we get that 20 grams will dissolve in 100 grams of water. Because remember, this axis is in 100 grams of water. Now, my question particularly asks us for 300 grams of water. So what are we going to do? Well, if we know that 20 grams will dissolve in 100 grams of water, we can set this up like a proportion. So down here, you'll see we have 20 over 100 because 20 grams will dissolve in 100 grams of water. And that's going to be equal to some amount of grams over 300. So when I cross multiply, I get that X is 60 grams. Because it's very easy to see that 300 is 3 times 100, some of you might also be able for this particular problem to just say, okay, 300 is 3 times 100. So if 20 will dissolve in 100, 3 times 20 is 60. You can solve it either way. All right, another way to ask this question or to use the solubility curve, at what temperature can you dissolve 50 grams of lead nitrate in 100 grams of water? So this time, instead of going to our temperature axis, I'm going to go to our grams axis. So I'm going to go to 50 grams, and I got to go to lead nitrate. So lead nitrate is right here. So I follow that 50 gram line till I get to lead nitrate, and now I'm going to my temperature axis, and I see that it is 15 degrees Celsius. Something else that we can see on our solubility curve is if a solution is what we call saturated, unsaturated, or supersaturated. So these are three kind of vocabulary terms that we need to know. The first, saturated, is the maximum amount of the solute is dissolved. We could not put any more into that amount of solvent at this temperature. So on a solubility curve, that is represented by the actual curve itself, the line. So for example, if we're talking about potassium chlorate, anywhere on this line would be considered saturated. Our next term is unsaturated. So just like the name suggests, it's not fully saturated yet, so there's less than the maximum. So that's going to be anywhere below the line. So if, again, we're talking about potassium chlorate, then any amount below the line for potassium chlorate is going to be considered unsaturated. And then we have something called supersaturated, and that is actually when more than the maximum amount is dissolved. And that's going to be represented by anywhere above the line. So for potassium chlorate, that would be anywhere above that line. Now, you might ask yourself, how in the world do we get a supersaturated solution? Usually, the way that's going to work is by heating the solution to a very high temperature, dissolving as much as will dissolve at that very high temperature. So if we're still talking about potassium chlorate, maybe we dissolve all the way up to 45 grams. And then we slowly cool it down. And if you cool it down slow enough, that 45 grams will remain dissolved. But notice at this lower temperature, that's above the curve, so that is now supersaturated. I always like to use the example of like any super sweet tea, like Bojangles or McDonald's sweet tea. If you've ever made it, you have to heat it up really, really, really hot to dissolve that ton of sugar. But then over time, it cools down, they pour it over ice, you drink it, it's super sweet. But if you were to, say, take that same amount of tea at cold and try to add the same amount of sugar, it's not going to dissolve. That's like northern sweet tea. If you try to take unsweet tea and add sugar, it doesn't work very well. So we can also be asked questions about if something is saturated, supersaturated, or unsaturated. So for the example, this says if 25 grams of sodium chloride is dissolved in 100 grams of water at 40 degrees, is it supersaturated, unsaturated, or saturated? So for this one, we are going to go to 40 degrees. We are going to the sodium chloride line, and then we are going to 25 grams. So we look here, 25 grams at 40 degrees falls below the sodium chloride line. And so this particular amount would be an unsaturated solution. We would be able to add more sodium chloride, and that more sodium chloride would dissolve. All right, guys, that is it for today. So today we are continuing to talk about solutions, but today we're going to focus specifically on something called concentration. And this is something you've heard before. You've probably heard something's very concentrated or something is very dilute. You may even see, like in the grocery store, there are some cans of soup that say like soup concentrate. That's because they're super concentrated and you take them home and add water to them. So concentration is just how much solute is dissolved in the solvent. And for chemistry, we use the unit molarity to measure concentration. So molarity is defined as the number of moles in 1 liter. So molarity are moles of solute over liter of solution, which is moles over liters. And we represent molarity with a large M. So a large M stands for molarity, and it's the same thing as saying moles per liter. Anytime we have molarity, we can kind of think of it like another mole conversion. Because if we multiply molarity, which again is moles over liters, if we multiply that by the volume in liters, that cancels out and we're left with moles. So if we need grams, we can convert moles to grams, or we can go grams to moles if needed. Another reminder, because this is in moles per liter, if you have milliliters and we need to convert it to liters, we just divide by 1,000. So the big things here, molarity is moles per liter, and we do know that we can convert grams to moles, moles to grams, and we can convert milliliters to liters if needed. So if we were looking to calculate molarity, it says, what is the molarity of a solution made by dissolving 20 grams in enough water to make 1.25 liters of solution? So remember, in order to do molarity, we need moles and we need liters. Well, here we have liters, but the problem is here we have grams. So I need to convert that to moles first in order to have moles over liters. So I'm going to take 20 grams of potassium chloride. We all know by this point to convert that to moles, we just use the molar mass of potassium chloride, which is in 1 mole, and we get 0.165 moles. Now we have both things that we need for molarity. We have moles and liters, so we're just going to put moles over liters, and we get 0.132 molar. What mass of sodium fluoride is needed to make 2.50 milliliters of a 2.45 molar solution? So for this problem, we know the molarity, which remember, molarity is moles over liters. And then we also know the volume. This time it's in milliliters, so we are going to have to convert it to liters. Okay, so to convert that to liters, we just have to divide by 1,000, so 250 becomes 0.25 liters. So now we know we have 2.45 moles per liter, and if we're going to go to mass, grams of sodium fluoride, I know I need moles. So from the information given, how do we figure out moles? Well, we're going to multiply our molarity, which is moles per liter, by our liters, which we said were 0.25, and that gives us moles. So 2.45 moles per liter times 0.25 liters gives me 0.613 moles. Now my question asked me for mass, which is grams. So in order to go to grams, we know that 1 mole of sodium fluoride is 42 grams, and so we multiply and get 25.7 grams. So if I wanted to make this solution, I would literally measure out 25.7 grams of sodium fluoride, and I would dissolve it into 250 milliliters of water. Next question, you need to make a 1 molar solution of sodium chloride. You have 10 grams. What volume do you need? So we're looking for volume. We're given molarity, which again is moles per liter. We're given grams. So we know we're going to have to convert that to moles. So we take 10 grams of sodium chloride. 58.5 grams are in 1 mole of sodium chloride, and that gives me 0.171 moles. So now I know my moles and I know my molarity. So if I have 1 molar, which is moles per liter, equals 0.171 moles over how many liters, I'm just going to solve for liters, and I get 0.171 liters, or 171 milliliters. Those are the same thing. Another type of calculation that we can do with solution concentration are called dilutions. So to dilute something, we're just adding more solvent. Again, this is usually water. So you can think of this like if you're making Kool-Aid and you put your package of Kool-Aid, you put all the sugar in there, but you only put half the water it calls for. You are going to have a very, very concentrated Kool-Aid. So then you realize your mistake and you add water. Now we have diluted it and we have a less concentrated Kool-Aid. So when we dilute something, we add more solvent. Remember, molarity is moles over liters. We're keeping the moles the same. I didn't add any Kool-Aid. I didn't add any solvent, or excuse me, solute. But I am increasing my amount of volume, and so my molarity is going to decrease. So our formula for any dilution is M1V1 equals M2V2. And all we mean by those ones and twos is that this is the molarity or the concentration before dilution. This is the volume before dilution. This is the molarity after dilution, and this is the volume after dilution. And the reason this formula works because, again, if we do molarity, which is moles per liter, times liter, we're left with moles. And as we just said, the moles are going to stay the same, so all we're doing is saying moles equals moles. So for example, we have 25 milliliter sample of a 12 molar solution of HCl, and it is diluted to the volume of 500 milliliters. What is the final molarity? So we are solving then for M2. All right, so I'm going to plug in M1, which is 12 molars, V1, which is 25 milliliters. I'm going to set that equal to M2 is my unknown. That's what I'm solving for. And then V2 is 500 milliliters. As long as both volumes are the same, I can keep them in milliliters. So I'm going to solve for M2, and I get 0.6 molar. So let's do some more practice. Maybe pause the video at this point, try these three on your own, and then resume the video to see if you got them correct. So for the first one, we have M1, we have M2, and we have V2. So for this first one, we were solving for V1. So I'm going to plug everything in, and I get that V1 was 0.25. In the second one, we have V1, and then we have V2 and M2. So for the second one, we were solving for M1. When we plug everything in, we get 4.8 molar. For the third one, we have V1, M1. We have V2, and we're trying to find M2. So when we plug everything in, solve for M2, we get 0.28 molar. So what you're going to do is you're going to do a lot more practice now with calculating molarity or doing calculations with molarity, and then practicing doing calculations with dilutions. And that's all for notes today. All right, y'all. So today we are switching gears from solutions to talk about acids and bases. So we're going to talk about how we name acids and bases, some of their properties, how they react with one another, and how we calculate their pH. So first of all, we need to know how to name acids and bases and be able to recognize which is which and write their formulas if we're given the name. So first of all, acids are always going to start with hydrogen. So if you see a compound and it starts with a hydrogen, so H and then something, that is an acid. So then how we name it is based on this something. If that something ends in ate, so like sulfate, phosphate, nitrate, we change the ending to ic acid. So if we see H2SO4, we know that SO4 is sulfate. If you forget, you just look up SO4 on your polyatomic ion sheet and you'll see that its name is sulfate. So that 8 becomes ic acid. So this is just sulfuric acid. The anion ends in ite. So for this example, we have sulfite, could be nitrite. Then we change that ite to ose acid. So hydrogen with sulfite just becomes sulfurous acid. Now the way I like to remember those two different ending changes is I remember I ate it, and that kind of sounds like changing ate to ick. And then we've all heard someone say, I got the itis, like that bronchitis, I got the itis. So that change, that kind of helps me to remember that I change I'd to ose. That's just how I remember it. The last example is if this something right here ends in I'd. Whoops. I just realized I wrote I'd up here. I meant to write ite. So ite becomes ose. Our last type of name is if this ends in I'd. So for this example, when we have hydrogen with sulfur, that would be hydrogen sulfide. So this time we actually don't just change the ending, but we also add a beginning of hydro and then change the ending to ic acid. So we have hydrosulfuric acid. Now, the reason why we have to have these different names is because if you look over here, sulfuric acid, sulfurous acid, and hydrosulfuric acid, all of them have sulfur. So we have to have some way of distinguishing which exact version they are. So to recap, 8 becomes ic acid, ite becomes ose acid, ide, we actually start with hydro, then the element ic acid. So now if we're given the name, we just got to work backwards from the acid. So if the name is ic acid, then we know it came from the polyatomic ion 8 with hydrogen in front of it. If the ending is ose acid, we know it came from the polyatomic ion ending in ite with hydrogen in front of it. And if the acid is hydro something ic acid, we know it came from ide, which is either going to be hydrogen plus an element or cyanide. Cyanides are only negative polyatomic ion that ends in ide. Besides hydroxide, but if you put hydrogen with hydroxide, that just makes water. Only other thing to remember is hydrogen is always a +1 charge, so whatever we're putting it with needs to balance with +1. So hydrochloric acid, the hydroic acid tells me it's hydrogen with chlorine. And hydrogen's +1, chlorine's -1, so HCl is balanced. This nitrous acid tells me that it's with NO2. NO2 is -1, so we've got +1, -1, so it's just HNO2. If I have phosphoric acid, the ic acid tells me it came from 8. So we have hydrogen plus phosphate, which is a -3 charge. So if we have +1 and -3, we crisscross, and that gives me H3PO4. Now, bases are super easy. Bases are just named like any other ionic compound. They always end in hydroxide. So if an acid was H blank, then a base is always blank OH. And so we literally just name whatever's in that blank and then hydroxide. So if sodium is in that blank, then it's sodium hydroxide. If magnesium is in that blank, it's magnesium hydroxide. Now,
hydroxide is a -1 charge. So when we write the formulas, everything is getting balanced with a -1. That's why for this first one, it was just NaOH because it's +1, -1. But for the second one, magnesium is +2, hydroxide's -1. So we had to put that 2 over here outside the parentheses. All right, so let's look at some properties of acids. First of all, acids taste very sour. Think about citrus fruits. They're sour fruits. Acids will conduct electricity when they're dissolved. When we put most metals into an acid, we're actually going to make bubbles of hydrogen gas. Talked about how acids always start with hydrogen. So when an acid is in water, it's in solution, it's going to make H+ ions. And if we're talking about the pH scale, acids are going to have a pH below 7. We have 2 tests for acids and bases we need to be aware of. The first is called litmus paper. So if we have an acid, we're going to put blue litmus paper in there, like in this picture, and it's going to turn red. There's also red litmus paper, but if you put red in an acid, it just stays red. So we're going to use blue, and it's going to turn it red. There's also an indicator called phenolphthalein, and in an acid, phenolphthalein is clear. So some examples of commonly known acids: vinegar, soda, coffee, citrus fruits, and wines. Base properties. Bases taste very bitter. So soap is an example of a base. If you've ever gotten soap in your mouth, it is very bitter. Just like acids, bases will conduct electricity when dissolved. They feel very slippery, typically. Please call the main office. Thank you. Sorry about that. They typically feel slippery like soap. We said that bases are something with hydroxide, so they produce hydroxide in solution. On the pH scale, they're going to be greater than 7. So for bases, like you see in this picture, red litmus paper is going to turn blue. So I always remember blue, base. And if we use that indicator phenolphthalein, it's actually going to be pink if it's basic. Some example antacids, so like Tums, you take them when you have acid reflux, so the base is going to neutralize it. Chalk, soap, drain cleaner, lots of our cleaners, those are all going to be basic. Now we're looking at acids and bases and we want to compare their strength. So we have something called strong acids and bases versus weak acids and bases. And what makes them strong or weak is how much they actually break apart or dissociate in water. If something is a strong acid or base, it's going to 100% completely break apart and dissociate in water. So however much acid we have, every bit of it is going to break down into H+ and whatever else it's made out of. Whereas weak acids and bases, they're only partially going to dissociate. So only a little bit of it's going to break apart. So if you look at this example, on this side, we have a strong acid. So we're starting with all acid, but in the end, we end up with only it broken apart. Whereas for our weak acid, we start with all acid, and we end with mostly acid and only a little bit broken apart, and that's what makes it weak. We have 6 strong acids that we need to be aware of: HCl, hydrochloric acid; HBr, hydrobromic; HI, hydroiodoic; HNO3, which is nitric acid; HClO3 is perchloric acid; and H2SO4 is sulfuric acid. Our strong bases are any group 1 hydroxides, so all the group 1 metals with hydroxides, and then our very soluble group 2, so that's strontium and barium. So these are our only strong acids and strong bases. Anything else is going to be considered to be weak. So now let's talk about what happens when we put an acid and a base together. This is also referred to as a neutralization reaction because we're taking something acidic, pH less than 7, we're adding it to something basic, which has a pH greater than 7, and in the end we end up with something neutral. This is a special type of neutralization reaction. So if you remember back to our reference table that has all the different types of chemical reactions, if you look under double replacement, the second one says acid-base reaction. So an acid and a base are always going to combine together to create a salt, which if we remember, salt is just another word for ionic compound, and water, both of which are neutral. So for example, look at this. We have hydrochloric acid and sodium hydroxide. The chlorine from the hydrochloric acid is going to combine with the sodium from the sodium hydroxide to form this ionic compound. Then our other product comes from the hydrogen and the hydroxide, which just makes water. So I have given you 3 equations to try. The first 2, I gave you the reactants, the acid and the base. We know this is the acid because it starts with hydrogen, and this is the base because it ends with hydroxide. So you need to write the 2 products. So the salt or the ionic compound and water. For the very last one, I gave you names, so you're going to have to write those formulas and then write the products and balance the equations. So we'll pause for a minute, try this on your own. Don't forget to balance the new products and balance the whole equation. So for the first one, we have magnesium combining with bromine. Magnesium is +2, bromine is -1. So when we crisscross it, we get MgBr2. Of course, our other product is water. Now, if we look at the whole entire equation, on the left, we had 1 bromine, but on the right, we had 2. So I had to put this 2 in front, but that gives me 2 hydrogens plus these 2 hydrogens, which made 4. So I had to put the 2 here. That gives me 2 oxygens, but that's good because I had 2 oxygens over here. For the second one, lithium is going to combine with sulfate to make our salt. Lithium is +1, sulfate's -2. So to crisscross, we get Li2SO4. And then, of course, again, our other product is water. We have 2 lithiums here, so I had to put a 2 there. That gives me 2 oxygens, so I had to put this 2 here. That gave me 4 hydrogens, but that's good because I had 1, 2, 3, 4 over here. For this last one, first thing I have to do is write my actual acid and base. Now remember, if it's ic acid, that means it came from 8. So that's why, if you look here, I have hydrogen with nitrate. Nitrate is -1, hydrogen's +1, so this is balanced. Calcium hydroxide, calcium is +2, hydroxide's -1, so when I crisscross, I get CaOH2. So now calcium and nitrate are going to combine, +2 -1, so I had to have CaNO3 plus my other product is always water. When I balance this, had to put a 2 out here to match this 2 nitrates. That gives me 2 plus 2 is 4 waters, which is 4 here, 2 oxygens, 2 oxygens. So now I am balanced. So when we're talking about acids and bases, we're going to talk about something called pH, which you've probably heard of before. If you've ever been around a pool, it's very important that the pH stays the same. Your body depends on its pH staying consistent. So what exactly is pH? pH is a measure of the concentration of hydrogen ions. So we can represent that with H+ in brackets, because brackets just means concentration. So like we learned earlier in this unit, we measure concentration in molarity, which is moles per liter. So in any solution, we're going to have hydrogens and we're going to have hydroxides. So the more hydrogen we have, the less hydroxide we're going to have, which is going to make it a low pH and make it acidic. The more hydroxide we have, the less hydrogen we'll have, and so it's going to have a high pH and be more basic. If hydrogen is equal to hydroxide, that is when we have a neutral solution. So the pH scale goes from 0 to 14. So 7 here is neutral. Anything lower than 7 is acidic. Anything higher than 7 is basic. This word alkaline is just another word for basic. One thing to remember, the pH scale is logarithmic. So that means if you have one difference in pH, like if you go from 5 to 4, that was a 10 times difference in your concentration. Now, we are going to do some different pH calculations. Be aware that all of these equations are on your equation sheet. When we have pH and pOH and add them together, it's always going to equal 14. The way we find pH is to take the negative log of the concentration of hydrogen. You literally click the negative button on your calculator and then the log button and then put in whatever number that is. Same for pOH, except it's the negative log of hydroxide. We have a constant called Kw, that's 1 times 10 to the negative 14. Whenever you multiply the concentration of H plus times the concentration of hydroxide, you're always going to get this number, 1 times 10 to the negative 14. And then if instead of having the concentration of hydroxide, if we have, or hydrogen or hydroxide, if we have pH or pOH instead, we can do 10 to the negative pH to get hydrogen, 10 to the negative pOH to get hydroxide. Now, if you look over here, this is a different way to kind of put this. And you can figure out where you're starting and where you're going, and that will help you figure out how to get there. So for this first one, what is the pH of 3.4 times 10 to the negative 5 molar HCl solution? Well, where are we starting? We are given the concentration of HCl, which HCl is an acid. So that means we are starting with concentration of H+, and we're trying to go to pH. So this is the formula that we need to use. And we see that right here on our equation sheet. So we figured out we were given an acid, and we were given the concentration of it, so that was the concentration of H+. So our equation is that pH equals the negative log of H+. So we take the negative log of 3.4 times 10 to the negative 5, and we get 4.47. This is an acid, so a pH of less than 7 makes sense. We have a strong acid with a pH of 2.65. What is the concentration of H+? So this time, we are given the pH, and we're trying to go to the concentration of H+. So this time, we have to use the formula, concentration of H+ equals 10 to the negative pH. So I'm going to plug that into my calculator. I'm going to raise 10 to the negative 2.65, and I get a concentration of 0.0025. Now, this one's a little bit trickier. What is the pH of 0.0010 molar sodium hydroxide? Now, this time we've got to recognize that we have a base. So this 0.001 molar is the concentration of hydroxide. And then it asks me for pH. So if I have the concentration of hydroxide and I'm going to try to go to pH, I have to actually do 2 steps. So first I have to find the pOH, then I have to find the pH. So in order to find the pOH, I'm going to take the negative log of that hydroxide concentration. That gives me 3. And then I use this formula, pH plus pOH equals 14. So pH is 14 minus pOH. 14 minus 3 is 11. Now let's think about that for a minute. We decided that this was a base, so a pH of greater than 7 makes sense. If the pH of a KOH solution is 10.75, what is the concentration of hydroxide? So this time we're actually starting with pH and we're going to the concentration of hydroxide. So we're going the other way. So the first thing we're going to have to do is we're going to have to find the pOH and then find the concentration of hydroxide. So our pH is 10.75. So in order to find the pOH, I'm going to do 14 minus 10.75, which gives me 3.25. So that's my pOH. And then to find the concentration of hydroxide, I'm going to do 10 to the negative POH to get 5.6 times 10 to the negative 4 molar. This one is actually asking me to find all four things, H+, OH-, pH, and POH. But now I am given 0.00562 molar HBr. HBr is an acid, so that means what I'm given is the concentration of H+. So I'm first going to go to pH, then I'm going to go to POH, then I'm going to find the concentration of hydroxide. So I have 0.00562 molar. When I take the negative log of that, I get 2.25 as my pH. Then I'm going to do 14 minus 2.25 to get 11.75 as my POH. Then finally, I'm going to do 10 to the negative POH, so 10 to the negative 11.75 to get 1.78 times 10 to the negative 12. All right. So now at this point, you're going to do lots of practice on this, okay? But that's all for our notes today. All right, y'all. We're in our final set of notes for this unit where we're going to talk about something called a titration. And a titration is a lab technique that often uses acids and bases. So a titration is a lab technique that is used to take a solution of known concentration in order to calculate the concentration of an unknown solution. We typically use acids and bases for this because we can easily see when the reaction is complete by using indicators. For all titrations, we have two parts. We have the titrant, which is the thing with known concentration, and we have the analyte, which is the thing with unknown concentration. So typically the analyte is going to be in a flask, and the titrant is going to be in something called a burette. A burette is a piece of glassware that measures volume very precisely. It allows you to open and close this little switch here. When you open it, the liquid will come out. When you close it, it will stop. So when we are doing a titration, the titrant is going to be added until it has reacted fully with the analyte. We call this point when it has fully reacted the equivalence point. So if our titration is between an acid and a base, and for this class it will always be between an acid and the base, then the equivalence point is going to happen when the moles of our acid equal exactly the moles of our base, because at that point the reaction is fully complete. It's totally neutralized. So we can take our initial volume, our known constant of the known concentration solution, the volume at our equivalence point, and we can calculate our unknown concentration. So the formula for this is MAVA equals MBVB. And the A is for acid, and the B is for base. So these calculations are pretty simple. It's very, very similar to the dilution calculations. We're always going to know three of these variables, and we're going to solve for the fourth one. Now, the way that we are visually going to see that we've gotten to the equivalence point or very close to it is by using an indicator. And the indicator is going to change color when the pH changes. So when we switch from acidic or basic. And we know then that we have passed our equivalence point because we have completed the reaction and gone to the other side. So where the color exactly changes is called the end point. And we want the end point to be as close to the equivalence point as possible, but it's always going to be just slightly past. So one common indicator that we use for acid-base titrations is phenolphthalein. So phenolphthalein is clear when it's in acidic pH, but it is pink when it's in basic. So in this picture here, this titration, we're starting with an acid and we were adding in a base. And when our color very slightly changes to light pink, We know that it's now basic, and so we have reached the end point and just slightly past the equivalence point. When we do these acid-base titrations, we can actually track the pH, and that's going to create what we call a titration curve. So it's going to track the volume of the titrant added on the x-axis compared to the pH of the solution on the y-axis. When we get to this major jump, that's where we're switching from, in this case, acidic to basic. So right in the middle of that jump where the pH is 7, that is our equivalence point. So wherever the equivalence point is, we know that's the exact volume that was needed to get there. So that's going to be the volume we use in our MAVA MBVB calculation. When we have a strong acid being titrated with a strong base, which is all we're going to use for this class, that equivalence point is always going to be right at 7, just like I showed you on the last slide. So let's look and see what these calculations can look like. So we have a 31.7 milliliter sample of 0.65 molar nitric acid. It's titrated with, whoops, well, that is a typo. It's not going to affect our problem, but nitric acid is definitely not HCl. The nitric acid is titrated with 0.82 molar lithium hydroxide. How much lithium hydroxide is needed to reach the equivalence point? Now, we know our equation at equivalence point is MAVA equals MBVB. For this particular problem, we were given the volume of the acid. We were given the molarity of the acid. We knew the molarity of the base, and we were trying to find the volume of the base. So we're going to plug in everything we know, solve for the base volume, and we get 25.1 milliliters. All right, so for this next problem, let's pause the video, take a minute, try to identify which parts you have of MAVA equals MBVB, and solve for the missing. You should have figured out that you were solving for the molarity of the base. So we plugged in the volume of the acid, the molarity of the acid, we plugged in the volume of the base, we solve, and we get that the molarity of the base had to have been 0.14 molar. For this last problem, we have 45 milliliters titrated with 1 molar, and we are given the following titration curve. Well, what information do we need from this curve? We need the volume at the equivalence point. So that's going to be 25 milliliters. So pause this for a second and try to solve the problem. So for this one, we were calculating molarity of the acid. So we knew volume of the acid was 45. We knew that volume of the base was 25. And molarity of the base was 1. So when we solve for molarity of the acid, we get 0.63 molar. So now you are going to practice doing more of these titration calculations at the equivalence point with your formula MAVA equals MBVB. All right, y'all, that is it for Unit 9. Only one unit left.